Our next speaker is John Roberts from the University of New South Wales, and he'll be speaking about combinatorial models for integral birational maps over finite fields.
Thank you very much. And of course, I'd like to thank the organizers. You've done a really good job to adapt to the circumstances, so thank you. So my abstract was quite general, and this is not entirely what I intended to talk about. That'll have to wait for another talk. But the second half of the talk will be work that is actually being written up with my former PhD student, Tim Sue, who successfully completed his PhD in 2019. So this talk is in a similar theme, and we'll review some history of things that you might have seen me talk about in the past. So we're studying discrete dynamical systems from a set to itself. And initially, the idea would be we would be studying these over a continuum, a space that's a continuum, like the complex or real numbers. But as in approach taken in number theory, which are called sort of global local approaches, the idea is eventually to look at the dynamics over a finite space, in particular finite fields. That's what F sub P is. It's the integers mod P. And although I'm not going to talk about the true definition so much of integrability, Liouville integrability, obviously the starting point for showing a discrete system map is integrable, is to find some integrals. In other words, I'm using dash for my image point. I want to find a function that's preserved under the dynamics. And I always like to give Holger a plug when I talk about such things. He has a lovely talk where he talks about the journey that he goes on to try and figure out if a particular map has an integral. And doing this over the reals or complex can be very subtle. There are various things you can do. The most obvious thing you would do would be to draw a phase portrait and try and see if your dynamics is living on a lower dimensional space than the ambient space, and in particular, does it appear to be lying on a surface or intersections of surfaces? There's various other sort of checks that you can do, which are numeric, and in this story on the net, Holger in particular looks at eigenvalues of periodic points to many digits. We heard yesterday from Ralph about singularity confinement, which is often used as a method to infer integrability. Of course, Claude Violet and others have developed algebraic entropy approaches. And I guess all of these are about singularity confinement and growth in complexity are about trying to have a quick diagnostic as to whether it's worth spending your time on a system to see if it's genuinely integrable. The approach I'm going to talk about here, which is arithmetic, is the one I'm going to focus on. And most of the maps, or a lot of the maps that we talk about are birational, and we're often interested and find that the integrals are rational functions. So this means we're in good place to use number theory and algebraic geometry. There is a tyranny of working over the continuum, which is part of searching for integrable systems. So here are three plots of this map L1, which for delta equals 0, that's the middle plot. For delta equals 0 is what we call a QRT map. So it has a definite rational integral. And you can see that the orbits lie on curves, which are the level sets of this rational integral. On the left-hand side, if I take this parameter here, delta equal to 1, I get the typical phase portrait you'd expect for an area-preserving planar or measure-preserving map. The beautiful interweaving of KAM curves, so non-algebraic curves, and also bands of chaos in between them, centered around hyperbolic periodic orbits. But the interesting thing perhaps is that on the right, by virtue of the KM theory, where the parameter is 10 to the minus 4, you see up the top, the picture is almost indistinguishable from the true integrable case. So this is a problem of working over the continuum, in this case, the continuum, the parameter space. And to speak anthropomorphically, integrable systems are special, and of course, they would like to be recognized as such. They would like to have their identity validated. Now, it turns out I can relate to this. My name, John Roberts, is very common, and I'm eternally grateful that my parents gave me 2 middle initials, because even John A. Roberts in the science literature, there's thousands of them. But, you know, in the last couple of years, you can have issues of identity, and you can wonder if people are really talking about you when they say things like this, or you can feel pressure to make the world a better place. So these are global examples of John Roberts. But I even have local examples of John Roberts. My university has decided to, like lots of universities, improve its branding and update our websites. That it's taken the interesting approach of updating all our websites and doing it live without actually getting us to check the result. So this means that if you have more than one John Roberts at your university, then you can get a website like this, which is this esteemed Professor John Roberts in the business school, and yet it has my address, his email address, his phone number, and my biography. And, this is a source of some mirth to both of us, but it is starting to have consequences. He sent me a message last night saying, looks like I'm giving an interesting talk next week at this university. And if you look carefully, you'll see on the left there, it's his picture, it's John A.G. Roberts, and I'm talking about retail reset in post-COVID era. And even at the bottom, it helps if the talk is in Turkish as well. So there are lots of challenges to finding the real identity of something. And to make it easier for integrable systems, we're going to work over a space that's discrete. So I want to concentrate on the last space here, the product space of F sub P to the D. So I think we all know what the orbit of a point is, and we know that a point is periodic if you some iterate returns you to that point. And it's called pre-periodic if there is a little pre-tail. So in other words, you start off and then you reach a point which is periodic. So it looks a bit like a tadpole, and some people call it a row shape because of the Greek letter. Now, pre-periodic points have a finite orbit, and if the space is finite, then you've a finite number of places to go, and you must come back to somewhere you've been before. So in a finite space, all orbits are necessarily pre-periodic. And so this talk and this approach is largely about taking a system that's defined over a continuum and looking at it over a discrete space. So for instance, take the polynomial x squared minus 1 mod 11. You've now got a space, it's got 11 points in it, and you can draw this function graph that tells you exactly that 5 goes to 2, but also 6 goes to 2, so non-invertible, etc. You can figure out everything you want to know about this, but of course, 11 is a very small prime. Now, we're familiar with toy models like studying quadratics have been key to advancing study of complex dynamics, think Julia sets, think Mandelbrot sets. But you can also study the dynamics arithmetically, and it turns out this has a very practical application. The integer factoring algorithm, in other words, factoring an integer into primes, one of the most famous is Pollard's row algorithm, and it's precisely called row because of this idea that over the finite space, you have these pre-periodic points. at some point in the model, you have to ask yourself, how does x squared plus 1 act modulo a prime? And it turned out to be a very good assumption, very good heuristic to say that it acts like a random map on the finite field with an expected recurrence time of order root p. And now heuristics based on pseudo-randomness and associated probabilistic models abound in number theory, arithmetic dynamics. We saw a nice talk by Michael Wheeler yesterday where they come up in random matrix theory, statistical mechanics. So way back in 2003 with Franco Vivaldi in London, we began to study arithmetic dynamics of Hamiltonian dynamics and associated properties. So the idea was, if you're looking for a property over the continuum, and if this property can be expressed algebraically so that it makes sense in the reduction when you go from the complex or reals to the finite fields, then you can look for inferences or signatures of those properties. Of course, most interesting maps that you deal with are not polynomial, they're rational, and they'll have singularities where the denominators vanish. And the upshot of this work was that we found that there were some universal and signature distributions and behaviors that you couldn't prove for an individual map, but worked very well as heuristics. And the other advantage of working, say, over finite fields is that if you're working in parameterized spaces, your parameter space is also discrete. And so it's rather easy to find the needle in the haystack, which is the integrable, truly integrable system, because it stands out because something like delta small over a finite field is just some other random residue. Okay. As part of this, and I talked about this maybe a couple of years ago in this forum, Tim and I developed a fast diagnostic that gives an inference on the number of integrals or rational integrals in a birational map. And then you can actually do a little bit more work to try and push to see if you can see the footprint or the signature of Liouville integrability. Now, I should say also there is some lovely work being done in a large group that includes Reinout and Peter van der Kamp, Reinout Crispel and Peter van der Kamp, using Darboux polynomials, which actually works in the original space, making certain ansatzes and looking for rational integrals. Okay, so if you go back to the picture, remember over the continuum, the integral map was, and the close to integral map, the dynamics was living on lower dimensional varieties because of the existence of integrals. Now, when you go to a finite field, you no longer have a curve, but you still have the idea of a variety. In other words, the curve is defined as a polynomial vanishing on a certain set, where the set now is in fp to the n. And there are results that tell you how many points that you can actually see on this variety. So if you're working in a d-dimensional, if you have an ambient space with dimension n, and you have an r-dimensional irreducible, that basically means it doesn't factor, algebraic variety of degree d, you have this bound on the number of points that can be accommodated on this variety. And if you just take the case where you have fp n equals 2, this is the famous Hasse bound, that the number of points on elliptic curve is bounded by p plus 1 plus 2 root p, p plus 1 minus 2 root p from below. So in the past, I've talked about how you can exploit that to check, actually usually used as a necessary condition to throw out lots of possibilities in a parametrized family for a map being not having an integral. So for instance, if you take a map, let's take two maps, the Henon area preserving map, and let's take, say, a QRT map. And for each P, you just calculate the longest orbit that you can see over this finite space. And then I'm going to scale by this Husserl bound, which is the largest a number of points I can have over an elliptic curve in a finite field. So I can't have an orbit, since if I'm really integrable, I can't have an orbit that's longer than the whole number of points in the curve, then it's an effective bound. And you see that since I've scaled by that, you see that along here is the green data. This is showing that the QRT map always has a longest orbit bounded by this Husserl bound. However, it's very obvious, and it's very obvious for a map that's not integrable, to immediately see that it has longer, much longer orbits generically. And so if we go back to the picture I originally showed you of over the continuum, the delta equals 0 picture looked very much like the delta equals 10 to the minus 4 picture because of KM theory telling you that when you perturb an integrable system, many of the curves remain in the perturbation. However, if you started with an algebraic curve, it will become transcendental on perturbation, so that these bounds, Husserl bounds, don't apply. And so this is again a very startling picture that shows that the scaled length of a particular, you choose an initial point, you take its orbit mod p, and you scale it by this Husserl bound, and you see that you come in under 1 for the genuinely integrable one, and you're all over the place, well above 1 for the one that is not. Okay, and just illustrating the point that close to integrable over a finite field, it doesn't mean anything. You're either on the money or you're not there at all. Now, as I said, it's nice to have a quick inference as to whether a map has integrals and how many it might have. So take a map that's birational over R to the D. Assume it's also reversible, which is sort of almost has to be generic if it's going to be a candidate for being integrable. In other words, that means that it's the composition of two involutions. And if it's birational, then these component involutions are going to have singularities. Because if something is reversible and you look at a periodic orbit, you can ask, is it invariant under G or is it not? If it is, we call it symmetric. If it's not, it'll come with a partner, which is its image under G. Now, when you go down over a finite field, you can look at the fixed sets of these involutions. And when you look over a finite field, you can count how many points you have on this curve. And I'm going to call that G. And you can count how many you have in the fixed of H. And then you have denominators, which are going to give you singularities in the map if they vanish. And so when you bring those denominators down, they're also curves over a finite field, and you can count how many points you have on those curves. In fact, you know from Husserl type bounds, you know the order of how many you have. So let's suppose you want to know how many rational integrals this map might have. J is, it could be 0, it could be in dimension 5, and it could have 2 integrals, etc. So we came up with a method to define this thing J star. And it involves looking at the reduction of the map, mod P, and then just looking at the periodic orbits and checking if they're symmetric or asymmetric. So are they fixed under the reversing symmetry or not? And then just counting the number of asymmetric periodic orbits you get. And then you have these various functions here, and here D is your ambient dimension, and here are the cardinalities of these sets I described. Now, if this is going to be a reasonable model, the whole point is J star should be close to an integer. And the other thing is, it shouldn't really depend on P, because if you're taking the same map and it has two integrals upstairs, then when you take reductions mod P, the number of integrals you see should not change. So, we found this formula gave very good inferences for maps that we tested in various dimensions that had various numbers of integrals. You see that as a function of P, this is J star, and you see it's fairly horizontal, and it has pretty much integer values, or certainly good enough that you could make a pretty good inference as to what integer the J might be. Okay, so that's all seems a little bit magical. Where the heck did this formula come from? Well, it came from making heuristic assumptions about pseudo-random behaviors of maps over finite fields. And that's what I want to go on to talk about now, and to talk about a particular model and to look at its statistics that come from it. So to give you some flavor of this, this map here is the Henon map. I talked about it before. It's a map of the plane, and it's polynomial, obviously, it's invertible, and it's also the composition of involutions. You can check that one of the involutions is interchanging x and y. And the whole idea of looking at its dynamics mod P is to take parameters, there's a parameter in here, A, and phase space variables as residues mod P. Because this is invertible, because it's polynomial, you're going to get a complete decomposition of the P squared points. And you can build yourself a distribution function for the induced permutation and its periods. So you just do the sort of obvious thing to build a cumulative distribution. You count, this is the dimension of the space, and you count the proportion of the space that is consumed in periods that are less than or equal to kappa x. And kappa is a characteristic scale length that you should measure periods in, particularly if you want to go asymptotic. And in this case, kappa is the average number of, that's the average length, which turns out to be P, order P. Okay, so then if you plot this distribution, so this little scratchy thing that you can see here, you can see two curves here. The scratchy one is this result of building this distribution function for P equals 997. And underneath is a limit we conjectured at the time, this smooth curve, which is this function R of x. And incidentally, R was not chosen for Roberts. This was not the identity crisis. R was chosen for reversible, because we thought this is characteristic of the fact that the map upstairs is the composition of two involutions. All right, now, if you now slightly modify that map, and I put another parameter in here, delta, then in R2, this would be, if you take delta less than 1, this would be what's known as the Henon dissipative map, which has the famous strange attractor. For our purposes, over FP2, this is still going to induce a permutation, but it's not going to be, it's going to be irreversible. So you do exactly the same thing, and you build a distribution function. Now, what happens is that the characteristic length of the periodic orbits is much larger. So the periodic orbits here are much larger than the previous case, and so there's less of them. And if you take this characteristic length here, p squared, then you essentially get the y equals x. That is this IP of x equals x is this distribution. So all of this led to a sort of idea or presentation which sort of mimics, in some sense, random matrix theory, that when you take maps with certain properties upstairs, and then you look at their reductions, and you look at period distribution functions, you see a distribution that has a certain universality that doesn't depend on the details of the map, but it's guided by a certain property of the map. So here is, if the map was non-integrable and irreversible, this was this curve I just looked at, which of the right scaling is y equals x. If it was reversible, this is this function I called r of x is 1 minus e to the minus x times 1 plus x. And if you now impose even more order and you impose that there's a rational integral, then the Husserl bound and all sorts of other algebraic geometric properties like equidistribution kick in, and you find that your distribution function is quantized. You see, when it's flat here, that means there can be no periodic orbits with this scaled length. And so you can only have periods that are clustered around divisors of whose length is clusters around a divisor of the Husserl length. Okay. These signatures also worked as good necessary conditions to detect algebraic properties. But now I want to think a little bit about the models, because basically the thing I even showed you for suggesting the number of integrals is based on building up a series of models and developing a heuristic. Now, suppose you have the left-hand picture here. So you have the Henon dissipative map. What do you think is a good model for its dynamics? In the absence of anything else, you might think that a map that's well defined everywhere should act like a random permutation. And so, in fact, we tested that on this map I just presented and tested various known characteristics of random permutations, and indeed, they seem to be numerically verified. And of course, an enormous amount is known about random permutations. So how do you build a model and what do you do with it? Well, let's start with supposing we have the symmetric group. So we have all the permutations of n elements, and we're restricting ourselves to a particular subset of it because of some constraint that comes from a property that forces us to live in this subset. Then basically we're going to build a distribution by averaging over that subset. The physicist would say we're creating different ensembles and we're going to calculate distribution functions over these ensembles. And so this is just the formula that you have to build this distribution. And the thing that you have, and incidentally, this is an expected distribution. Okay, so you're just going to, you're looking for results in expectation. And so if I take the whole symmetric group, then it's well known that the probability of getting a period from 1 to n is the same, independent of t, that's 1 on n. And then in expectation, if you go and build this distribution, you get x, which is what we were sort of seeing in that picture before. Way back in 2009, Franco and I looked at, now let's take the subset of the permutations that are composition of two random involutions of S sub n. with particular constraints on the fixed sets of these involutions, but they're fairly broad constraints. That as n grows, the size of the space grows, so does the cardinalities, the sum of the cardinalities of the fixed sets, but they don't grow fast relative to the space. And then we showed that in expectation, we would get exactly what we hypothesized was the distribution R of x, 1 minus e to the minus x times 1 plus x. So that was satisfying, but just showing that something holds an expectation, although it's very common to many fields now, it can often be impossible to show that you actually get that result for a randomly chosen element in the ensemble. However, for random permutations, you do have some very strong results that tell you that as n goes to infinity, the measure of random permutations that will have these particular characteristics, that goes to 1. So they're very tightly bunched around the expected behavior. Anyhow, this was all about, our original calculations were done with polynomial automorphisms. And of course, then we branched into rational and birational maps. And so the question I want to just talk about now, which is what we're writing up right now, is what's the equivalent of a random permutation, or what's a good model if now we are looking at genuinely birational maps. So now I'm going to have my k-coordinate functions, I have numerators and denominators, and I have assume I have an inverse map, which is also rational. So my map is birational. And as I said before, the whole point is that now, if I'm working in the affine space, I'm going to have points where I arrive to, and the denominators can blow up. And I'll be undefined. Now, if you think about it, over the reals or complex or over a continuum, any experiment you do with these maps, you hardly ever are troubled by the singularities, because you're never really going, you're going to lie close to them, but you're very rarely going to sample them. Okay. It's a different story when you go down to a finite field, because you are guaranteed to have a certain number of points on these curves. And so almost the opposite happens of what happens upstairs. The singularities run the whole show downstairs. And so we wanted to look at the effect of that. And so I say now that the model I'm describing now is just a piece that we had to put in to that eventual calculation of the expected number of integrals. And it's all about knowing what's the background behavior if we didn't have the integrals. So we defined this model. Suppose your space is the integers 1 to n, and for some integer s, choose subsets, so I'm going to call s and s bar of cardinality little s, and these need not be necessarily disjoint. And if you're in S, you're going to be called a singular point, and if you're in S bar, you're going to be called an origin point. Otherwise, let's say that you are, your map is a bijection. So what's going to happen? The space is going to decompose into S strings that start in S bar, and you can't go backwards from S bar, and terminate in S, and you can't go forwards from S. And I'm going to call that part of the space n sing. And then you're also going to have some J cycles. You're going to have a number of cycles. That number must be between 0 and n minus s. And I'm going to call that part of the space n psi. And I'm going to create an ensemble of these functions, and I call them S-cut permutations. And with a little bit of combinatorics, I can count the size of this ensemble using n choose S and using a falling factorial. So what do I mean by S-cut permutation? Well, everything I just described can be taken from a permutation. So here in this picture is a permutation of 31 elements with cycle lengths 4, 5, and 22. And the red, I draw it as a directed graph, and then I'm going to introduce red cuts, if you like, and I'm introducing 5 of them here. And when I introduce a cut, I create a point that I can't, that has no prehistory. So 13, why is it 13 here? Here, yes, it is. 13 is here. Okay, so this is an origin point, and then I go until I hit a cut. So 8 is what I call a singular point, and that's in S. Okay. And you see what happens when I do these cuts is I get string lengths of this length, and I get a 5 cycle. So Tim and I went and looked at the expected behaviors that you would get with such a model. And so now let me build this distribution function. So it's the probability that a point lies in a singular orbit, a string of a certain scaled length. And I put an assumption on the number of cuts I've introduced. If, as the space goes to infinity, the number of cuts goes to infinity, but not too fast. And then interestingly, this distribution is exactly, in expectation, the distribution that we had originally for a reversible map, but that had some structure in it. Remember, the random permutation was supposed to be the map, the model for something that had no structure. And now, by the way, how much time do I have left?
About 1 or 2 minutes.
Thank you very much, Pete. Yeah, so this was a little bit thought-provoking. So the whole space is now consumed in singular orbits, asymptotically. There are no periodic orbits. And the distribution is following a distribution that we previously had characterized as a map that had a special property, like being a composition of 2 involutions. The proof is just working out sizes of spaces, probabilities, and doing some asymptotics. Recall that H sub n is the harmonic number is the sum of the reciprocals of the first n integers. And asymptotically for large n, this goes as log n plus this constant, Euler's constant. And this is actually the expected number of cycles for a random permutation. So if you took a random permutation of p-squared points, like you might get from the reduction of the Henon dissipative map, you expect basically log of p squared or 2 log p periodic orbits. Whereas if it's reversible, you actually expect around p periodic orbits. So this showing that for the reversibility gives you many more cycles and hence shorter average length. So now if you restrict yourself to the set that is made up of periodic orbits, you can ask yourself, what's the expected number? Even though you know asymptotically the amount of space they take up is going to 0. And you get this nice result that if this was a random permutation, you would have S equal to 0. If you define H0 equal to 0, then you would get the random permutation. Now you get the difference of these 2 harmonic numbers. And you can also calculate what the distribution of the lengths is within this space of periodic orbits. So you can do these things in expectation. And I wouldn't be talking to you if they weren't good heuristics. And this is just evidence that we went and checked these with real birational maps that didn't seem to have any properties, special properties, and these seem to be quite accurate heuristics. So just to conclude, I've given you one example of the model building that eventually goes into what we found in Tim's thesis and which we are now putting into papers. And we found the same distribution for birational maps with no special structure as reversible polynomial automorphisms. But then when we thought about this, we realized that this function is well known. This is a gamma distribution in statistics. And it turns out that the creation of periodic orbits in reversible maps and the creation of singular strings in these cut permutations are guided by the same sort of statistical model of hitting a target in forward and backward direction. And as I said, we're now writing up the other models for different key parts that led to this formula for J star. Okay, thank you very much.
Thank you very much, John, for the wonderful talk. Are there any questions or comments? Robert, please go ahead.
I'm just wondering if the continuous map has an invariant volume or symplectic structure. Does that survive when you pass to the finite case?
Look, I don't think so. I don't think so. Because, for instance, look at the Henon dissipative map. The determinant is less than 1 over the continuum. It's shrinking. But as far as looking over a finite field is concerned, it just looked like an invertible map.
Mm.
So things like being measure preserving, where, as you know, means that the Jacobian determinant can be written as a quotient of a function of x and a function evaluated at the image point. You see, that turns back into a variety type question. And I do believe that things like that are amenable. In fact, I'm looking at questions like that right now.
Thank you.
So this could be extremely useful. When can we expect an implementation in Maple of a function that tells me the number of integrals if I give it a map?
Well, you have the formula there, actually. So all you have to do is it's just a decomposition of the space and tagging whether take a periodic orbit and just for the known reversing symmetry, just take the image of that point and check if that was in the orbit or not. If it wasn't, then that's asymmetric and that goes into your count.
Holger?
Yeah, thanks, John, for a very entertaining talk. Identity crisis, theology, everything is in there. I just had a question about this formula for J star. If I read it correctly, if I turn it around and read it as a formula that counts the number of orbits that are asymmetric,
yes,
which I can do, then it seems to say that if I have more integrals, I have more orbits. Right? Because
yes, exactly.
And that seems completely counterintuitive, right? I would have somehow thought more integrals should give less orbits. But okay. I don't know, that's wrong. So why is it wrong?
Okay, no, so the key point here is to do with finding something, finding a quantity whose growth is not just polynomial in P. Because you know, for instance, suppose I give you a random permutation of FP3, yeah? And I ask you, it has no particular properties, how many periodic orbits do you expect? Well, you expect log of the cardinality of the space. So you expect log P cubed, yeah? Now, suppose I now tell you that that map has a linear, an affine integral. So in other words, it actually lives on the level sets of a plane. Now, within reason, you could argue that that is now p copies of a two-dimensional map. And so now how many, if it was random as a two-dimensional map, I would have expected log p squared. So if it has that integral, I'm going to see p log p squared, or I'm going to see 2p log p rather than 3 log p. And so that is exactly why you're using asymmetric things, because if you use symmetric, they actually just equidistribute across the integral. So if you had, if you had order p cubed of them and you put them on p level sets, they'll just come down to p squared. So the key seems to be to find something, a quantity that you can measure whose growth is not polynomial. And that is why the asymmetric orbits.
Cool, thanks. Yeah.
If I could follow up, how do you count the asymmetric periodic orbits when D is large? You mentioned something about random sampling.
Yes. So, I mean, you can try and do, obviously doing a complete decomposition of the space becomes a pain. So you can start to do a sort of Monte Carlo type approach. And sort of if you've sampled efficiently or well, you can build an inference based on what you've sampled.
Thank you very much again, John.
Yep. Thank you
Wonderful
very much.
talk.